Hello and welcome back. Today we're going to be going over the very first question of algebraic geometry by Robin Hartshorne, as you see on the screen there. Uh, Without further ado, let's begin. This question wants us to show that the affine coordinate ring of the the algebraic set, we don't know it's a variety yet, but it is. The affine coordinate ring of the algebraic set defined by the plane curve y equals x squared, so just the normal parabola, is isomorphic to the the univariate polynomial ring over K. We're over some what's it called? Algebraically closed field K. So y is a subset of K squared, and y equals x squared. Well, what y is defined to be is the vanishing set of f, or the ideal generated by f, this question is mostly just a case of plugging in definitions. So what is defined to be the vanishing set of the ideal generated by f, uh, where where f equals y minus x squared, which is irreducible, and so this is prime, and so radical, um, as k adjoint x, y is a unique factorization domain. The affine coordinate ring A of y is, by definition, um, k of x, y, all divided by I of y, but this is I of the vanishing set of f, which by Hilbert's Nullstellensatz is the radical of f. But as f is irreducible, then the ideal generated by it is prime, so it is radical. So it is the same. Hence, this is equal to k of x, y, all over y minus x squared. Now, there is a canonical surjection. There's a canonical surjection k x y into a of y via how are we going to do this? Okay, c naught naught plus c naught 1x plus c naught 1 naught y plus c naught 2x squared plus c1 plus c2 naught y plus dot 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 maps to y squared, not y. C naught naught plus C naught 1x plus C1 naught y, x squared, because y equals x squared, that's what this is, plus C naught 2x squared plus C1 x cubed, because it's x times x squared, plus C2 naught x to the 4 plus dot 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 equals, and then you can just sort of put them together. Addition is always commutative, so you can put them together. So C naught naught plus uh, C, well, let's not call it C. Kappa naught plus kappa 1x plus kappa 2x squared plus kappa 3x cubed plus dot 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 dot, where kappa is the sum of I plus j equals, well, kappa, let's just say kappa n, n, I plus j equals n, cij. And this is very obviously isomorphic to k adjoin x. So we are done. Now on to 1.1b, which is the exact same question as before and the exact same method as before, but this a of y is going to be different. So a of z equals kx y divided by I of z equals, well, z is the vanishing set of xy minus 1. Xy minus 1 is irreducible, therefore I of z, same thing as before, k of x y divided by x y minus 1. Do. So, again, we basically write the same as before. So, kxy into a of z via c naught naught plus c naught 1x plus c 1 naught y plus c naught 2x plus c 1 1x y. This should be squared plus c 2 naught y squared plus let's go c naught 3x cubed plus c, just because it's much easier to tell the pattern here. And what we're going to see is x, y, oh god, I'm terribly sorry. What we're, goodness, what we are going to see is xy equals 1. Equals 1, not y. What? What is going on? Goodness. Equals 1. What? Ah, sorry, my arm is wet and I went against my pad, so it's a little bit broken. What on earth? One moment. Okay, that was strange. Oh goodness. Hopefully I can, yes, okay. So, x times y equals 1. So, c, what would this be? 1, 2, x squared y plus c 2, 1, xy squared plus c 3 naught y cubed plus dot 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 dot. Maps to c naught naught plus c naught 1x plus c 1 naught y plus c naught 2x squared plus c 1 1 plus c 2 naught y squared plus c naught 3x cubed plus c 1 2. X times y gets removed, so x plus c2 1, again, x times y gets removed, y plus c3 naught y cubed plus dot 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 dot. And what you'll see is the only thing that remains is pure powers of x and y. So it's let's call it kappa again. Kappa naught plus kappa 1x plus And you'll see why I am writing this now. Kappa minus 1y plus kappa 2x squared plus kappa minus 2y squared plus dot 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 dot, which is, oh, and x times y equals 1. So your instinct is, why have I done this? Well, this is actually isomorphic to k adjoint x comma x to the minus 1 as a ring, which, I mean, you can double check, but with the ring isomorphism theorems and just uh, x maps to x and y maps to x to the minus 1, but I mean, you should be able to see very easily why this is the case. But I think that we should move on to 1.1c, where this is a question essentially about the characterization of conics, or classification of conics, which are quadratic polynomials in two variables, or polynomials whose degree is 2. Now, we can write our f as ax squared plus bxy plus cy squared plus d x plus ey plus f. Now, this is a standard result from conic theory, I guess, from the study of conics. But if we write down a matrix, which is A, B over 2, B over 2, C, D over 2, D over 2, E over 2, E over 2, F. Now, if the determinant of this, or if the value of this is equal to 0, then F is a F is not fun. Wait, I'm terribly sorry. My mind is drawn a blank. If it's equal to 0, then F is reducible, so we don't want it to be 0. Therefore, our conditions on F are this is not 0. Now, if this is not 0, then we can define a quantity called the conic discriminant, which is b squared minus 4ac, which, if you've done anything above a GCSE level maths, I don't know what it would be in other countries. If you're about 16 and you've done maths, you should be able to recognize that somehow, which, yes, if c equals 0, well, no. Wow, sorry, breaking the fourth wall there. So a equals, let me just see, because, okay, sorry. Well, if this discriminant is, let's say, less than 0, then, I don't recall which one means hyperbola, which one means parabola, and which one means ellipse. I know that perhaps parabola is equal to 0. It doesn't matter. So, parabola is equal to 0. If this is equal to 0, then you can do some linear change of coordinates, or some change of coordinates which are of the form x goes to ax plus b, where a and b are constants and y a similar way, and you have f kind of looks like x squared minus y, or y minus x squared. The parabola. And if x is, I do forget which one is elliptic, which one is hyperbolic. Ah, I see. I am terribly sorry. My notes are very strange. I'm working from notes. Basically, if it's equal to 0, then it is a parabolic conic, so it is somehow able to be transformed into y equals x squared via those transformations. And the same for elliptic means that you can change it into a circle. X squared plus y squared minus 1. Parabolic means that we can change it into y minus x squared. And hyperbolic means that we can change it into xy minus 1 via those linear changes of coordinates, which to be fair, I could just check. Okay, this is greater than 0, this is less than 0, this is equal to 0. Oh my goodness, I should have realized that because curvature, ellipses are negatively curved, or, well, spheres are negatively curved, but I should have realized that. Or I could have just plugged it into the equation. But we have answered this, we have answered this, we need to answer this. And it's a fact that if you change coordinates linearly, like, not even linearly, if you affine changes of coordinates, if you change your coordinates in an affine manner, which means x, y goes to some matrix times x, y plus some vector, then your affine coordinates are the same. And it just so happens that you can always change it to that. But we need to check what the affine coordinates of the nah, of the unit circle are, which we can do now. So let W equal the vanishing set of x squared plus y squared minus 1, which is prime, so a of W equals to kxy all over x squared plus y squared minus 1, or equal to kxy all over I of W, which is the ideal generated by functions which vanish on W. I should have said that. This is the equivalence classes of functions which don't vanish on W. That's what the affine coordinates rings of the affine coordinate ring of an algebraic set is. But we have k, x, y map to, or surjectively mapped to A of W via C naught naught plus C naught 1x plus C 1 naught y plus C 2 naught 2x squared plus C 1 1xy plus C 2 naught y squared plus um, C naught 3x cubed plus C 1 2x x squared y plus C 2 1x y squared plus C 3 naught y cubed. And I am going to, well, x squared plus y squared equals 1. Ah, I see the issue here. Well, it's C naught naught plus C naught 1x plus C 1 naught y plus C 1 1xy plus, well, I'm just going to have to sacrifice one of y squared and x squared. So we say, yeah, C, let me just redo this. Alpha naught plus beta naught y plus alpha 1x plus beta 1xy plus alpha 2x squared plus beta 2x squared y plus dot 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 dot, which as a module is isomorphic to kx. Direct sum of kx times ykx. I am almost certain that if we change u equals x plus iy and v equals x minus iy, then, but that's what's in my notes, then a of w changes to alpha naught plus changes to kappa naught plus kappa 1 u plus kappa minus 1 v plus kappa 2 u squared plus kappa minus 2 v squared plus dot 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 is isomorphic to k adjoin x to the minus 1, or u to the minus 1, but the two would be isomorphic with a with the whatever it's called, with the assignment u to x to u. Oh, and what I should say is this is the ring of Laurent polynomials in x or over k. but we can see then A of W here is isomorphic to K adjoin X, X minus 1. A of W would be isomorphic to K adjoin X. And finally, A of W would be isomorphic to K adjoin X, X to the minus 1, which provides one more link in the great number of links between spherical and hyperbolic geometry. So think of X and Y here as, I believe, just cos and sine, and U and V as sine and cosh, but I could be wrong, because cos of Z is e to the I Z plus e to the minus I Z. Hmm, I'm not certain. But either way, this is what we should have. So 1.1c, f equals ax squared plus bxy plus cy squared plus dx plus ey plus f. Then if w is the vanishing set of f, I should say z here is what Hartshorne uses. The vanishing set of the ideal generated by f. Z is what Hartshorne uses, but I use V because I think that vanishing set is prettier than zero set and can't be confused for the z-axis. So W is the vanishing set of the ideal generated by F. Well, if this very fun A, B over 2, B over 2, C, D over 2, D over 2, E over 2, E over 2, F, if that is not 0 and delta equals 0, then A of W is isomorphic to K adjoint X, and delta is not equal to 0, then A of W is isomorphic to K adjoint X, X to the minus 1. And that is all three parts of question 1.1. I don't have a drawing, but I I can make one now. I'm not as good as my fiance. Thanks for watching. Goodbye.